Hello, everyone. In this section, we will introduce the current mechanisms inside semiconductors in electronics. First, let us understand what electric current is. Electric current is the flow of charge. What kinds of charges exist inside a semiconductor? As introduced in the previous section, a semiconductor contains electrons in the conduction band, holes in the valence band, and immobile space charges. Among these, the mobile charge carriers are electrons N and holes P. To make charges move, a driving force is needed. One type of charge driving force is an electric field. An electric field applies a force to charged particles and causes them to move. The current produced by charge motion due to an electric field is called drift current. Another mechanism that makes charges move is caused by non-uniform charge distribution in space. This non-uniform concentration creates a concentration gradient and leads to diffusion. The current produced by charge diffusion due to non-uniform concentration is called diffusion current. First, we introduce drift current. As shown in the figure on the right, a voltage source V is connected to a semiconductor crystal, and a horizontal electric field E pointing to the right is produced inside the semiconductor. Positively charged holes move to the right along the direction of the electric field. Negatively charged electrons experience a force in the opposite direction of the electric field, so the electrons move to the left. First, let us look at holes with equivalent positive charge. The velocity produced when holes move under the force of an electric field is called drift velocity. Experimental results show that this velocity is proportional to the electric field's strength. Therefore, the relationship between drift velocity and electric field is obtained. The hole drift velocity, Vp, equals mu p multiplied by electric field E. This mu p is called hole mobility. Mobility describes the relationship between electric field strength and carrier drift velocity. It represents the ability of carriers to move under the force of an electric field. In silicon, hole mobility is about 480 square centimeters per volt second. After obtaining the hole drift velocity, we can obtain the hole drift current density. This current density is the amount of moving charge per unit volume multiplied by the velocity in the direction of motion. This gives the charge flow per unit area in that direction, which is the current density. Therefore, the hole current density is ρP multiplied by Vp. The volume charge density of holes is the number of holes per unit volume, which is the hole concentration P, multiplied by the charge of each hole, plus Q. Since drift velocity equals mobility multiplied by electric field, the hole drift current density is Q times P times mu P times E. Similarly, let us look at electrons. Electron drift velocity is also proportional to electric field strength, but the direction of motion is opposite to the electric field direction. Therefore, the relationship between velocity and electric field has a negative sign. The electron drift velocity, Vn, equals negative mu n multiplied by electric field E. Mu n is the electron mobility. In silicon, electron mobility is about 1,350 square centimeters per volt second, which is about 2.5 times the hole mobility. This is because the effective mass of electrons is lighter than that of holes. This belongs to the field of solid-state physics. Therefore, the electron current density is ρn multiplied by Vn. The volume charge density of electrons is the number of electrons per unit volume, which is the electron concentration N, multiplied by the charge of each electron, negative Q. Substituting the electron drift velocity, Vn equals negative mu n times E, we obtain the electron drift current density as Q times N times mu n times E. We can observe that the direction of electron drift current is also the same as the electric field direction. Finally, the total drift current inside a semiconductor equals the hole drift current plus the electron drift current. Therefore, as shown in the equation, J drift equals Q times P times mu P times E plus Q times N times mu N times E. This can also be written as Q times E times the quantity mu P times P plus mu N times N, which equals sigma times E. Sigma is the conductivity. Therefore, the conductivity of a semiconductor equals Q times the quantity mu P times P plus mu N times N. The reciprocal of conductivity is the resistivity of the semiconductor. From the equation, we can see that semiconductor conductivity is strongly related to the internal carrier concentrations, including electrons and holes. As introduced earlier, the electron and hole concentrations in a semiconductor can be changed by doping donors and acceptors. This is a major advantage of semiconductor materials. Doping can be used to control the conductivity or resistivity of a semiconductor. Next, we discuss diffusion current. The figure on the right uses a semiconductor with non-uniform hole concentration as an example. The concentration is high on the left and low on the right. Carrier diffusion moves from the high concentration region to the low concentration region. Holes carry equivalent positive charge, so the direction of hole motion is the direction of current. They move from left to right. In a one-dimensional coordinate system, the positive x direction of current is usually defined as positive. In the charge distribution shown in the figure, the concentration gradient, which is the slope of the concentration curve, is negative. Therefore, the hole diffusion current is proportional to the negative gradient of positive charge concentration. The positive charge concentration is the hole concentration P multiplied by the charge plus Q. A charge concentration gradient causes charge diffusion. The diffusion ability of holes in a semiconductor is described by the diffusion constant, dP. D means diffusion, and P indicates holes. The unit is square centimeters per second. This constant represents the diffusion ability under the same concentration gradient. A larger value means faster diffusion, higher diffusion velocity, and a larger diffusion current. In silicon, the hole diffusion constant is about 12 square centimeters per second. Finally, we can obtain the formula for hole diffusion current. It is negative Q multiplied by the diffusion constant multiplied by the gradient of P with respect to x. If the concentration gradient is negative, the hole diffusion current is positive, as shown in the diagram. Next, let us look at electron diffusion current. Similarly, as shown in the figure, assume that the electron concentration is high on the left and low on the right. This means the concentration gradient is negative. Electrons diffuse from the high concentration region on the left to the low concentration region on the right. However, current direction is the direction of positive charge motion, which is opposite to the direction of negative charge motion. Therefore, the current caused by electrons diffusing to the right points to the left. Since current in the negative x direction is negative, the direction of electron diffusion current has the same sign as the concentration gradient. Jn diff is proportional to Q times the gradient of n with respect to x. Similarly, the diffusion ability of electrons under non-uniform concentration is described by the diffusion constant, dn. Inside silicon, the electron diffusion constant dn is about 34 square centimeters per second. Finally, the formula for electron diffusion current is charge Q multiplied by the diffusion constant multiplied by the electron concentration gradient. If the concentration gradient is negative, the electron current is negative, as shown in the diagram. When we compare the electron diffusion current formula with the hole diffusion current formula, we can see that the hole diffusion current formula has a negative sign. This means the sign of the current is different from the sign of the concentration gradient. For electron diffusion current, the sign of the current is the same as the sign of the concentration gradient. The total diffusion current inside a semiconductor is the sum of the electron diffusion current and the hole diffusion current. Finally, we combine the two current mechanisms introduced in this section, drift and diffusion. We can obtain the total current formula inside a semiconductor. The total current is the sum of drift current and diffusion current. Among these parameters, mobility affects the carrier drift velocity in an electric field, while the diffusion constant affects the carrier diffusion ability under a concentration gradient. These two parameters are actually related to each other, and this relationship is called the Einstein relationship. The Einstein relationship states that the electron diffusion coefficient divided by the electron mobility is a constant, kT over Q. kT over Q is also called the thermal voltage. At T equals 300 Kelvin, kT over Q equals 25.9 millivolts. This value is positively related to temperature. Similarly, the hole diffusion coefficient divided by the hole mobility is also the constant kT over Q. That concludes the introduction to current mechanisms inside semiconductors. Please look forward to the content of our next class. See you next time. Bye-bye.